Thanks for playing along. Okay? So actually, I thought since I have this up, I might go ahead for the next few slides and kind of take these definitions of an acid and base and kind of put them on here. Again, this is my first time to do this. We have 3 definitions coming up. We have the Arrhenius definition, and some of this will kind of fits in the context of kind of what people think anyway, which is kind of nice. Okay, the Arrhenius definition, it says an acid provides a proton. Oh, by the way, notice how I slipped into chemistry jargon here. Anytime you see an H+, that is actually a hydrogen ion, and a hydrogen atom looks like this, where it has 1 proton and 1 electron. That normal hydrogen has no neutrons. So the point here is that if you go ahead and strip away an electron and make it a +1 charge, all you have is a proton. So you're going to see me and actually other physical science people kind of slip into H+ is the same thing as a naked proton. Yes?
Now, it's been a little bit since I had General Chemistry 1, but did we talk about acids and bases at all? Okay.
Only, we talked about strong acids and bases. And the cool thing about strong acids, and actually that's on one of the slides we're going to talk about today, strong acids are great because there's no chemical equilibrium, but weak acids, it doesn't go completely to the right. It doesn't completely go one way, it goes back and forth. The weak acids, and that's why we're chasing a moving target, and that's why we have to use the equilibrium chemistry. So yeah, we did talk about them, but there were strong acids and strong bases. Cool. So according to Arrhenius definition, if something, and this is kind of neat, we'll be talking about donating, okay? Something donates a proton or something donates, do you remember what the name of this is?
Hydroxide.
Yep. That's the hydroxide ion. Something donates a hydrogen ion, it's an acid. Something donates a hydroxide ion, it's a base. Okay, so this is donates. Okay. Oh my goodness. It's just got issues today. So that's Arrhenius. Bronsted definition. I think it's got like a little dots over the O maybe, or the E, I don't know. But we'll just go Bronsted definition. Is similar. An acid is one that donates a proton, donates a hydrogen ion, and a base is one that accepts a proton. And we'll call this a proton donor. Guess what we call this? A proton acceptor. Okay. So now, these written right above each other, what does H+ and OH make? OH minus. What does that go to form?
So it's just, is that H2O?
H2O. And that's kind of part of the equation too. Actually, that's in chemical equilibrium. So, oops, my arrow. Okay, so now I actually switched a few slides around. This slide is a few slides from now, but we talked about chemical bonds. We talked about covalent chemical bonds where electrons are shared, ionic chemical bonds where electron is transferred. So covalent bonds where electrons are shared. Now, a coordinate covalent bond is a covalent bond that's formed when one atom provides both of the electrons that are creating that sigma or pi bond. And the example we've got coming up looks like this. I'll draw a Lewis structure. Dun, dun, dun. If I were to draw, let's see, NH4+, what is that?
Ammonium.
Ammonium, very good. It's not ammonia, it's ammonium. If we were to come up with, well, I'll just do it this way. I'm going to draw nitrogen in the middle and the 4 hydrogens coming off. Now, nitrogen, I'm going to draw electrons representing the valence electrons around nitrogen atom. It's 5a, so there are 5 valence electrons. So I'm going to make those circles. 1, 2, 3, 4, 5. Okay, so those are nitrogen's 5 valence electrons. Now I'm going to shimmy up a hydrogen, and I'm going to make its electron an X. And it's kind of a long story. I didn't go through this process with you for drawing Lewis structures, but as it turns out, the pot of valence electrons, this is how the Lewis structure looks. Where this guy right here, that guy right there, both electrons came from the nitrogen atom, okay? The other ones, one came from the nitrogen, one came from the hydrogen. Of course, I draw this final Lewis structure, and it looks like this. And these are sigma bonds, hydrogen, 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 hydrogen. And don't forget, if you're drawing a Lewis structure like this, it's charged. You have to put it in brackets. Okay. So, but like this slide says, once it's formed, there's no difference between that coordinate covalent bond and those other normal covalent bonds. But that kind of leads us to this last definition. The Lewis definition is one where the acid accepts an electron pair from another substance to form a coordinate covalent bond. So acid accepts, I'm just going to put dot dot for my pair of electrons from another substance to form coordinate covalent bond. And a base provides that dot dot, that pair of electrons. Provides dot dot to form coordinate covalent bond. So let's see what that looks like. Now, in acid-base chemistry, there's a lot of kind of going back and forth between reactants and products. As I've drawn them here, these are going to be my reactants, and here in a minute on the slide, you're going to see the products. So the way to think of this is if I compare those two things, which is ammonia and hydrochloric acid, with the product side, which is ammonium and the chloride ion, what's happening from left to right is kind of those lone pair electrons associated with the neutral ammonia molecule. You can think of it that way, as providing the coordinate, the pair of electrons that form this special covalent bond between the hydrogen that is stole from the chlorine. So in order to make sense, I think, of acid-base equilibrium, you're always going to have kind of, I think you have to look at both sides. So one of the things you're going to, now this one might be a little tricky, this is our first one, but one of the things you need to be able to do is look and see what's acting as an acid and what's acting as a base. And again, to me, the best thing to do is to look on either side of the equilibrium arrow. So does this make sense that the NH3, the neutral molecule, must be acting as, notice that it's acting as electron pair provider, the Lewis definition, and it's also acting as a hydrogen, an H plus acceptor, okay? So actually, the NH3 fits both of these bills if you compare them left to right. And the Cl, okay, is actually acting as the H there, and the HCl is acting as the electron pair acceptor. That goes up here. And it's also acting as the proton donor. Okay, so that's kind of how that works.
Now, is there some substances that are always bases, always acids, or does it kind of just depend on the...
There are some substances that can be donors or acceptors, and we actually call those anthropomorphic. It's like the last slide in here. But usually one tends to do one more than it will do the other. Yep. And it'll get easier to identify which is which. Now, remember reaction, equilibrium arrows means it goes from left to right and also goes from right back to left again. So we actually could look at these two species, and I actually added this today. So if we're going from right back to left again, does this make sense that your NH3, and I usually go with the Bronsted. I don't like the Lewis. It kind of hurts my brain. So if you go with the whole proton, does this make NH3? I meant to say NH4 plus. Do you see where this NH4 plus is being a proton donor when you compare it to the NH3, and the Cl minus is being the proton acceptor? So that's why this is an acid and this is a base if you're going from right back to left again. So yeah, like I said, this one I put it up there, but I really like the Bronsted and I like the Arrhenius. I don't like the Lewis too much, but that's how it works. Okay. So in general, when we're talking about identifying something as an acid or a base, we are going to focus on, I think it's a little bit of a hybrid, but we're going to focus on this one. Okay. Notice though, if something creates the hydroxide ion, guess what hydroxide does? If it creates this, guess what it does? It will accept a proton. So, I mean, I think that's kind of covered too. My Doceri's just not happy. All right. Now, it's important. I was like getting ready for today's lecture. I'm like, I wonder if they know that. Well, of course, B stands for boron, but not here. Okay. This B is just some generic term. This B could be anything. This B could be, well, let's see, what would be a good example? It could be Cl. No, that's not a good example. I'm trying to think of a weak acid. It could be anything. It's a generic thing. But if we just generally say HB, okay, combines with water, it's in water solution, that's a matrix, okay. As it splits apart, this is the way I think of it, actually the H plus that's created as this splits apart, is going to grab onto a water molecule, it's minding its own business, and it's going to form something, actually there's a word for it coming up, called the hydronium ion. What's going to be left over? Well, the B minus, just floating around, something generic. Or something like specific, but the B minus is generic for it. In that sense, if we look either side, clearly, hopefully, this works for you. If you compare the left to the right side, the HB is being a proton donor. It's an acid. Okay? The H2O is being a proton acceptor. And this kind of goes to maybe what you were saying. Water is great. It's the strongest anthropomotic, oh, darn it. Whatever that word is, it could go either way. It can accept a proton, become hydronium ion, the H3O plus, or it can kick off a proton and become the hydroxide ion. Okay. Let's just for kicks, let's see. Kind of what I did before, and I'm getting a little bit ahead, but if you look over on the right and go right back to left again, which of these would be the acid, the proton donor?
The H3O.
Yep, exactly. That would totally be the acid. And how do you know that? Because it's kicking off a proton as it goes like that. And then that would make this the base. And you can see where it's accepting a proton? Yeah. Okay. But instead of kind of showing that water molecule being involved with this acid to accept the proton this acid gives up, this is just kind of showing ionization. Just showing how this and this acid, and I know it's a weak acid because it's not a one, it goes back and forth. What we say ionizes or splits apart to a certain extent. How does it split apart? Well, what does it form when it splits apart? Well, your H plus, okay, and your B minus, which is something. B is just kind of a placeholder. Okay. Well, here in a minute, and it might be coming up soon, one of the neat things we know we can do about chemical equilibrium that we spend a lot of time in Unit 3 doing is we can write chemical equilibrium expressions. And that's exactly what we're going to do here. Okay. This is showing if you go ahead and have HB ionized to form H plus and B minus, that H plus can go ahead and find a water molecule and form hydronium. Okay, this is kind of showing it in a separate step. Okay, so a little bit of words here. The H plus is the hydrogen ion. Remember, I called it also a proton. And then finally, I've been using the word already, but that H3O plus 1, where a hydrogen ion has found a water molecule, we call that the hydronium ion. Sometimes I'll call it the hydronium cation for some reason. I don't know. It's positively charged, but I don't know why I do that. Even if this is not shown, sort of think behind the scenes that is what your proton, that's what your H plus, that's what your hydrogen ion is doing, is finding a water molecule. Okay, so this is all to say that whenever we work chemistry problems, acid-base problems, these can be used interchangeably. The hydrogen cation, the hydrogen ion, and the hydronium ion. So where did I? Serious. All right. Sometimes, and this is one example in science, you're like, why do they have two ways to? I don't know. I think there are advantages sometimes to emphasize something and advantages other times. So yeah, you asked about Chem 1, and in Chem 1 we focused on strong acids. We assumed that when you get HCl as a strong acid, that it's all entirely ionized into your H minus and your Cl, your H plus and your Cl minus. Okay. Strong acid, and ionizes completely. And I hope you're okay with the word ionize. Ionize means splits apart. So I'll put all these up here, and actually I even printed this out for myself because I forget what these are. So you're going to want to know these. For each one of these, here's a one-way arrow showing it splitting apart into H plus and that B minus, whatever it is. Okay? And then last year I did it, so I just kind of left it in here. See if it works for us. BB stands for Breaking Bad. I wish Mike was here. But there's definitely scenes in there where, it's not going to let me do it. Well, I pushed it out on Twitter too. But where they use acid to dissolve bodies and stuff like that. So, yes.
Now with the sulfuric acid, does it kick off both of the hydrogens?
You are just full of good questions this morning, Olivia, or this afternoon. Actually, we're going to see the first one goes completely, and it leaves HSO4 minus 1, and the second one is a weak acid. So it just ionizes just a little bit. Yep, so very good. So these are all strong. But these are all strong, and actually these we're going to kind of set aside for a while now, and we just want to focus on the weak ones. The weak guys. So is this a strong, is HB a strong or weak acid here? 50-50 chance strong. Why?
Because does it pretty much have to kick it off? Or just one way?
Just a one-way arrow. Yep, just a one-way arrow. Yep, very good. Yep. So the two ways we kind of wrote the equilibrium for weak acids, we can write the reaction or ionization of a strong acid. We can show it finding a water molecule to form the hydronium ion, or we can just simply show it falling apart. Recognize that this H plus is running around in aqueous solution, is really finding water molecule and turning it into the hydronium ion. I think that's kind of fun behind the scenes. Okay. So this will come into play later too. These strong acids, one-way arrow. So in other words, you can count on the HB form, the stuck together form of a strong acid is basically not existing if it's a relatively dilute solution. So we can neglect the presence of that, and that's a player in the chemistry coming up. Okay, so weak acids. Then you definitely need to use a two-way arrow because they ionize, but then they go back together again. So they'll never entirely 100% ionize. Okay. So in other words, this is interesting. So like if you have I don't know if this, one way to think about it, if you have a strong acid like HCl and you have a 0.1 molar solution of it, according to the chemistry we did in Chem 1, let's just go ahead and do it this way. If this is 0.1 molar, okay, this is 0.1 molar, right? This is 0.1 molar, okay? Now, if we pick on something else, we have a bunch of them coming up. I cannot think of any weak acids. Acetic acid is weak, CH3COOH, okay? It is actually going to go back and forth. So that means that, does this make sense? That this is going to be my B part, and it's going to kick off that proton. So I got, this is the acetate ion, and H+. So this doesn't work. This will not be equal to 0.1 molar, okay? Because it's going back and forth. It's in equilibrium. And we did a little bit in Unit 3 talking about how you get these equilibrium concentrations. So the same steps we did in Unit 3 we're actually going to apply to Unit 4. That's kind of the big picture of what that looks like. Okay, so let's look at one. You know, Unit B, again, is generic. It could be acetate, like I drew up here. It could be something else. So we have to use a chemical equilibrium to show it ionizing. This is the one of two forms. This is showing the water accepting a proton to form the hydronium cation. This is the other one where we just show it breaking apart in chemical equilibrium, though. And when we talk about extent of ionization, we're talking about kind of the forward direction. How much does it form? How much does it break apart? Okay. So let's see kind of a little more what that would, let's see. The protonation of water by a weak acid. Now the word protonation, does it seem like protonation means you're adding a proton? It does. So protonation of water is something we've been kind of talking about to form the hydronium cation. It looks stepwise something like this, where we have electrons kind of going and coming and forming coordinate covalent bonds, maybe. So I've got a couple of things down here. Our choices are, we're going to kind of look at the left side. So which species is the acid and which species is the base? Which one's the proton donor? Which one's the proton acceptor? What do you think?
H2O is the acid.
H2O is the acid. Well, you need to compare it.
Sorry. Yeah, sorry.
Yep. So you think base too? Base? Yep, this is acting as a base because it's accepting a proton. Almost put base like BASS, like the upright base. And this is donating a proton, so it's acting as the acid. Very good. Okay, what about the other side? Which one is the acid, which one's the base?
H2O is the acid.
This one?
Or not H2O, yeah, that one.
It's the acid, and that makes this one the base. Very good. See, to me, you have to look at them kind of side by side. Very good. Okay. So here we go. Now, remember, I kind of complained about this. We have, like, the lowercase k is the rate law constant. The uppercase k is the equilibrium constant. Are you serious? And we had KCs, meaning the concentration is in molarity. We had KPs, meaning the concentration was in partial pressures. Now we have KAs, which means it's in, and we had KSPs, meaning there was the solubility product constant associated with an insoluble salt. Now we have a KA, and it's the equilibrium constant associated with a weak acid. So generic, it's always products divided by reactants. It's the same rules that we learned in Unit 3. Raised to their stoichiometric coefficients, okay? So there you go. Now, why didn't H2O appear here?
Because liquids and solids don't appear.
Because liquids and solids do not appear. Very good. All right. We could write it the other way, and the Ka expression looks like this. Okay, so in this case, what's the thing that's different is now we have the hydrogen ion instead of the hydronium ion in the numerator. But otherwise, it's the same. Do you need to be able to do both? I don't know, probably. They're the same thing. Okay, so here they are side by side. These are what I call Ka statements, or Ka expressions. But before I move on, now this is, I don't know if you'll think this is interesting, but it's kind of like the amount of this hydrogen cation, the molar concentration actually is what gives us our pH. So does this make sense that in all of this mess, when we're going to start focusing on what is the pH of your solution, we're going to say, well, what is the molar concentration of that H plus? Okay? This doesn't change, this doesn't do our pH anything, this doesn't do our pH anything, it's the molar concentration of hydrogen ion. It's actually going to give us our H plus, our pH. And it's the pH, the molar concentration of hydrogen ion, that actually gives it acidity, or if there aren't H pluses, instead there's an abundance of OH minuses, that gives us basicity. Okay, so we talked about the bigger the Ka, it means it favors the product side, right? Okay, so the product side in this case is it ionizing, or it forming H plus and B minus. So the bigger the Ka value means it's the stronger acid. I buy that. I like things where I'm like, well, that makes sense. Not everything does. I was, my intro students, I was asking them how they're kind of making it fit, and they're like, well, I just remember it's the opposite of what you think it should be. I'm like, yep, that's right. One of those days, huh? It's Friday. It's Friday. Gotta love it. So we have some tables, and actually you might wonder how far we're going to get today, and we're going to get to that last assignment slide, but the last 3 or 4 slides I'm going to hold over till Monday. So I'm going to kind of take that assignment slide and bring it up. But here are some acids, and this is why I printed this off. Check this out, okay? You're like, these are my strong acids. Do you see any strong acids there? Well, I do. Like those first ones are strong acids. And you know, sometimes so nitric. So SA stands for strong acids, and we will be using that shorthand. Okay. These other ones are weak acids. Weak proton donors. What else do I got? The other side is, we'll be talking about more about conjugate acid-base pairs, but I already, well, first off, a base, this is going to accept a proton. That's my favorite definition. Does it look like they would accept a proton? And here's where kind of start to think about how this works. I'm going to pick on this amide ion as a base. Let's see, if it accepted a proton, NH2, feel free to kind of think out of the box here, plus H plus, I'm going to show it in equilibrium. What does it form on the product side? NH3. That's what we mean by it's being a proton acceptor. Okay. So those over there are proton acceptors. Now we're going to see Ka values here in a minute. And actually they're ranked by increasing acid strength and increasing base strength. Now before I move on, let's go ahead and talk about, they're actually lined up by row. If I go over here next to ammonia, or excuse me, the amide ion, look what I have for its actually what we call its conjugate acid. So here's its base, here's its conjugate acid. They differ by a proton. And to me that kind of makes sense because they can kind of go back and forth a little bit. Okay? And this might get to kind of what Livia was like, now which way will they go? Will they donate a proton or accept a proton? Well, it is confusing, but maybe not. This guy, he has to accept a proton. He's not going to give off another H+. And this guy, he could accept a proton and form NH4 plus 1. So actually, I think he could go either way. All right. So that's a little bit getting ahead of myself, but so the low Kas down here, the 1.8 times 10 to the minus 12 for hydrogen peroxide, does that mean it's a strong acid or a weak acid? It's weak, because it means that the low Ka, the small Ka means that it did not go to form products very much. So that would be a weak acid, yep. And here are some bases. Now I can't remember if I'm going to get to this or not, but we use the Ka to show the equilibrium constant associated with the weak acid ionizing. We use a Kb. Are you serious? Another equilibrium constant. We use the equilibrium constant Kb to show the equilibrium associated with a weak base. Then, again, I'm getting a little bit ahead of myself, but this is hard to describe. We talked about, pHs, but there's something called, and it's akin to pH, but something called pK, or pKa or pKb, and basically we're applying a, what do they call it? I think it's just P function to the Kas. So anyway, more on that later. Okay, so here are some, the title says weak acids, we'll take their word for it. You should be able to take any one of these species and picture it kicking off a proton. So for instance, let's pick on, and I couldn't think of any weak acids. Now there's all sorts of weak acids. Let's pick on this one. Okay, hydrosulfuric. Now hydrosulfuric, nope, not listed. Okay, so if it's a weak acid. So you should be able to, and I kind of wish your homework made you do it so you're ready for the next part, but it doesn't. You should be able to take H2S and show it going to form the H plus and the B minus, which in this case, we've got H plus, and the B minus part would be HS minus. Does that make sense? Okay, you should be able to do that. And then also should be able to write the Ka expression. Okay, so that's the molar concentration of the H plus times the molar concentration of the HS minus divided by the molar concentration of the H2S. The H2S we call the unionized weak acid. Okay, and in this case, we could write is equal to that number right there. And this actually goes back to what Olivia was asking about the sulfuric acid, H2SO4. The first H plus kicks off at H2SO4 like that. And then actually in that case you end up with what? HSO4 minus 1. And then it goes on to kick off the second proton. And here you can actually see that's what this is doing. We could write HS minus, acting as an acid to kick off a proton. You know, if you start to write it, you're like, oh yeah, that makes sense. And what's left is an S2 minus. Does that make sense? Yeah. Oops. It's mad. Wow, that's a new one. So anyway. Okay. What else we got? So those are the A's through H's. Okay, those are the H's through the T's. These are all weak acids. They're arranged alphabetically, not by strength in this one. Okay. You might need these tables, but you probably want to get them from your book because they're not quite so tiny. Okay, bases. The definition, the Bronsted definition of a base is it's a proton acceptor. A strong base is one that generates at least 1 mole of the hydroxide ion. Oh my gosh, the most common one is sodium hydroxide. You know, and again, and I think we used this, you guys had an experiment where you made your own solution of sodium hydroxide. We use a one-way arrow. So this could be 0.1 molar, this would be 0.1 molar. And to me, I kind of see the Arrhenius and the Bronsted definition kind of merging a little bit, because we actually did this in lab, that hydroxide in a water solution is great at accepting protons. Show equilibrium one way, but so I think those are not too separate from each other. So strong bases. Again, it's important that you recognize what a strong base is because it's going to have a one-way arrow and a weak base will have a two-way arrow, just like your strong acids and your weak acids. So hydroxide salts are pretty good. It says they're strong bases. So sodium hydroxide, ionizing completely, one-way arrow to form Na plus and OH minus. Now this is why the criteria said that you get at least 1 mole of hydroxide ion. Do you buy this, that we get 2 moles of hydroxide ion for calcium hydroxide? We get 2 moles of hydroxide for every 1 mole of calcium hydroxide we dissolve. Strong base. So, there are bases out there that don't have hydroxide as part of their formula, but they still create the hydroxide ion. The most common one is ethoxide. You're like, how do you start with something like this and get 1 mole of hydroxide ion? Well, it basically absconds onto a proton from a water molecule that it's swimming around with, and then it forms actually just ethanol. This is ethanol, okay, along with the hydroxide ion. It's kind of a sleeper. So the ethoxide ion is a strong base. Okay. But what we're most interested in are those weak acids and weak bases. The word hydrolyze, when I think of the word hydrolyze and actually I'm thinking of roquette and starch chemistry and stuff like that. I think of hydrolyze as kind of absconding onto a proton. That's kind of how I think of it. If I'm thinking, or I think of breaking a bond, I'll have to think. But anyway, it doesn't ionize completely, so we have to use a two-way arrow. So for instance, I think that works, hydrolyzing. You're going to see the deprotonation of a water molecule by your B minus there. It's going to abscond onto a proton or an H plus from that poor little water molecule. So proton acceptor. Okay, it's being a base there, like a good little base. So from left to right, you would say that B minus is acting as a base, proton acceptor. You would say that H2O water molecule is actually donating proton acting as an acid. You should get in the habit of, whenever you're looking at either side of the equilibrium arrow, you should find an acid and a base and an acid and a base. Okay. Well, this is showing it another way, without the Lewis structures. The B minus is going to actually act as your base here to accept a proton from your water molecule. And there's your KB expression. So we write equilibrium constant expressions for weak bases like this, where on the product side, you have your HB and your hydroxide ion, and the reactant side you have your B minus. Again, H2O does not show up. So there is your KB expression. But it goes the same trend as KAs. The smaller the KB means you don't have much of that product, and what that product is, I kind of think is that's what's making it basic, okay? That's the culprit driving our, ultimately, what we call pH here. Okay? So the smaller it is, the less this, and the weaker the base. All right. So here are weak acids and weak bases. I think we looked at that. Okay. Here are your weak bases down here again, and they're your KB values. And they are listed in order of increasing basicity and increasing acidity. But I like this slide because if you want to just kind of ponder something, look how these are being a proton acceptor, right? These are being a proton acceptor. And look how all these are being a proton donor. So, you have all sorts of examples to be like, oh, well, okay. The more you see, you're like, I get that. See proton, acceptor, you can kind of see from left to right how it's accepting a proton. And like I said, I kind of wish I was having you do more work with these, but that's okay. Ionization constants. See, I guess I buy that. So ionization constant, what is an ionization constant? It's a Ka or a Kb. What are we talking about? The extent to which your weak acid or your weak base ionizes. So there's another name for something that we already had a name for. Okay? Don't blame me. Okay, so we'll take a look at these two right quick. These shouldn't be too bad, but all homework is important. I was thinking about my 2 chemistry classes, and I'm like, I think I feel good about them because I really feel that because I'm teaching intro hybrid, I feel like intro hybrid and then this one that I give everybody the tools to make it work. Take a quick look at these, which isn't always the case in some classes. Believe me, I think you might have had some yourself, where you're like, I don't have the tools to succeed here. Okay, so this is the first one. It simply says, it tells you blah, 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 blah. say whether these are an acid or a base. And what I want you to do in your imagination is, do they look more likely to accept a proton, which they'll be a base, or donate a proton, which they'll be an acid? So my suggestions then, remember that you actually have all of those tables. Feel free to find them on a table, okay? So, let's see, what example do I give? Well, you can kind of see. Oh yeah, I guess the first one, I'm like, okay, does HNO2, does it look like it will kick off a high proton? Or does it look like it will take in a proton? And to me, this over here, I'm like, that doesn't look real likely, okay? So I'm like, oh, I bet it will kick off a proton. I bet it's gonna be a weak acid, okay? And feel free to find there, like I said, find them in the tables to help kind of answer that. For these, identify the acids and bases involved in the forward and reverse reaction. So I went ahead and did A for you, where I am looking for everything will have a label. So on the reactant side, you're going to find an acid base, and on the product side, you're going to find an acid and base. Okay. So very good. That's all I got. So we'll pick up with those last few slides and then tear into part 2 on Monday.
Have a nice weekend.
You too, Livia.